Lecture 36, and we continue our discussion on properties of filters with the help of 1D convection equation. We pick up a basically unstable Euler CD2 scheme, and we design a transfer function in such a way that we can modify the numerical amplification factor g with the help of this and solve this problem in a perfectly neutrally stable manner. However, in doing all this, we have already seen that basically most of the discrete computational methods introduce spurious upstream propagating waves, and this is the extreme form of a dispersion error. And as we have talked about, filters can alter the dissipation and dispersion properties. So, we need to relook at Q waves in the context of filters. But before we do that, we take a look at the G contours with and without filter, and we pick up some examples of rotary oscillation of a cylinder in a uniform flow, and we find out that if we perform a filtering in a particular direction, then these vertical structures actually elongate stretches in that particular direction, and of course, filter does attenuate the solution. So, we cannot avoid that. This can be somewhat mitigated by reducing the frequency, increasing the frequency of filtering, as well as considering the directionality of the filters in terms of azimuthal versus radial filter for this rotary oscillation problem. And we notice that azimuthal filters applied globally gives rise to serious issue. Now, in the following, we discuss about a new class of filters that we have designed, where the filters are themselves upwinded in the interior. Once again, this is done using Pardee schemes, and we work out the transfer function real and imaginary part and identify what is the alteration of the dispersion properties. And please note that in this particular effort, we are trying to alter the dispersion properties in such a way that we can remove Q waves. So, the motivation for this upwind filter design is to remove Q waves by a clever design of the filter itself. We also note that filters can be very interestingly used for large eddy simulation or detached eddy simulation used in fluid dynamics, because essentially filters does band limit the solution, and that is exactly what is done in LES, but LES is far too complicated a process where you actually filter the governing equation, and that brings in newer stress terms which have to be modeled. So, that could be completely removed by the present approach of using this implicit filters as a post processing operation. This should conclude our discussion on filters, and we can then begin our discussion on introduction to finite element methods, which is basically identifying the nature of global versus local methods and what are weighted residual methods. That is what we will briefly introduce and will conclude this lecture. I would still discuss a little more about filters, because that is related to one of your assignment, and I think this is one of the most beautiful tool that has emerged over last 15 years to do many things which were otherwise thought impossible. So, let us say if you are trying to solve a problem, an example, a convection dominated flow, and you take this model equation once again, and we know it is a property that it does not disperse, it does not attenuate, and you apply an algorithm, let us say, which we know is problematic, namely the central scheme in space and forward in time, and going through this motion of defining functions with respect to the Fourier Laplace transform, we define the numerical amplification factor taken with the help of the CFL number this is the algorithm that you actually use. And when you actually use the spectral representation of A in D, you get this, and this is what we have noted, that it's an unstable scheme. So what do you do? People have probably earlier thought that it's a no-win situation, but we will see today itself that by applying additional explicit filter, we can work out a stable algorithm, and maybe even a neutrally stable algorithm. That's one of the idea. So basically, if you have a solution obtained at an advanced time level, you want to filter it, indicated by this capped quantity, then we will define the amplification factor at the end of numerical integration and filtering is given by what you obtain after filtering, divided by the solution that you had before time integration, right. So this we split it into two parts, and you can notice that we have artificially introduced this factor u of kh at t n plus 1. So this is basically the output of your numerical integration. That is what we have called as the transfer function of the filter, right. So this is what the filter does. It takes this denominator and produces the numerator. So that's the transfer function. And then this is the basic numerical method by which you have reached t n plus 1 from t n. Okay. So this is the usual language with which we speak when we talk about explicit filters. We need to look at Tj of k. So show you a result which is somewhat different than what you are going to do in your assignment. Your assignment talks about propagation of a packet, but here we have looked at even a simpler problem, taken a domain, and we say that we have a periodic problem. So the periodic problem is something like this, a sinusoidal wave propagating, entering through the left and exiting through the right, so that you can use the same algorithm, CD2 Euler, and we know it's going to be unstable. But what we do is we apply a second order periodic filter, and for this combination of kh equal to 0.2 pi, if you choose delta t in such a way that nc is 0.1 for this value of c equal to 0.1, this choice of filter coefficient of 0.48 would make your method neutrally stable. So that if I identify one period of the wave by this solid red line here, that after a sufficient number of steps, when you reach at t equal to 30, it is identified here at the exit plane, and you see there is absolutely no attenuation here. So this should give you heart in thinking that filter is a technique by which you can take an unstable method and make it work. So this is one example that you are seeing here. Now there is something that we already have seen, and that is about this dashed region here in this figure and in this figure, where we are showing the group velocity normalized contours for this type of combination. So this is a 4-stage Runge-Kutta method used with that compact scheme that we have talked about, and this is the CD2 scheme with RK4. And as you see that replacing Euler by RK4 gives you a neutrally stable region, which is shown by this horizontally hatched region. But you can see that region exists over a very small value of kh. If you go a little on this side, what will happen is you will get a damped region, right. So that may not add to accuracy of the solution. That's what we talked about. Now when it comes to this spurious upstream propagating waves, which we have called the Q waves, the situation is worse when you look at CD2 scheme as compared to the compact scheme, and this is what we have seen earlier, some animations also, what this entails. today we basically are going to talk about that what filter can do to alleviate similar such problem. Okay. So, if I look at OECS3 RK4 scheme, on the right hand side you can see that the G contours are shown here in the KHNC plane, and you see only this region to the extreme left where you have neutral stability, right. Now, suppose I apply a 6th order filter with a value of alpha as 0.45, then this G contours actually change like this. What is interesting for us to notice that, of course, this neutral region degrades. You get a neutral region now which is sandwiched here only, okay. Whereas this 0.99 line that you could see here actually terminates up to here. And what is important for us to realize that for this higher value of KH, the filter actually attenuates it significantly. The filter effect that you would see mostly on this high KH range, even when your NC is small. Here we had a neutrally stable region, right, this part, but here it is all gone. The G has become close to 0, right. So, this is something we have to realize why filter is sort of welcome so often, because most of the numerical problem originates from high wave number region, and if there are problems, application of filter actually removes it quite drastically. However, you may lose accuracy of the solution. That is another issue that we have to keep in mind. Now, show you an example of a problem. This appears very simple. What you have is basically a cylinder, and this cylinder is performing some kind of oscillation. It is going back and forth. So, that is what we call by rotary oscillation. It is not just simple rotation, it is doing rotary oscillation. So, what happens, half the cycle, part of the flow on one surface will be opposing the convection direction. So, suppose let us say the flow is going from left to right here, then when it is going anti-clockwise, then the top surface you will have a opposing motion, and that opposing motion actually enhances the chance of flow separation. And in another half of the cycle, you will see a similar thing happening on the lower surface. And when you keep doing this, this cylinder keeps performing this rotary oscillation, you will see a very neat train of vortices come out, and these vortices are much stronger than what you are probably told if you have taken a course on fluid mechanics, if you keep a stationary cylinder. So, these are extremely strong vortices, and capturing this flow is not so easy. I will not go about CFD of that part, but what I am trying to show you here is basically look at this top figure where we have shown the lift coefficient, the upward force that the cylinder experiences as a function of time. And if you look at the 3 curves that those have been shown here, the solid line is the one that is obtained without using any filter, and it seems to go on, then at t equal to 47 it actually blows up. So, you see what happens is sometimes you have to really enlarge your window of observation to make sure that things are all right. Suppose I would have stopped at 40 and say, oh, I could get a good solution and I could present such results, but here it is clearly seen that at t equal to 47, all of a sudden the CL nosedives and the solution blows up. Why it does so? That is given in this vorticity contour plot. What happens is this is one of the vortex that has been shared in recent times, but prior to that there was another vortex that was shared from the lower side, which goes and convects downstream. And there are certain parameters of this problem is the amplitude of oscillation and the frequency of oscillation. Those are given by those A and FF. So, please do not bother too much about exactly about those parameters, but let me tell you, this flow is at a very low Reynolds number. It is as low as 150, and computing it is one of the toughest challenge that we have ourselves encountered. So, it just simply blows up, right. Now, what we could do is we could then try to use filter and see what happens. And this is what has happened here. We have applied a fourth order filter with a alpha value very close to 0.4. That is what is given here with this square symbol here. No, the one, sorry, with this dashed line with this solid symbol here. That's a fourth order filter, and goes to the value of alpha is 0.495. And what happens if you do that? The solution goes little farther, then again that also blows up. So this is something that we should keep in mind, that in actual flow computations, it's not like 1D wave equation that you are solving in your assignment. Everything is known, you can work it out. For a real problem, you would not know a priori what is the order, what is the filter coefficient that you have to choose. So here a choice of a fourth order filter with a alpha equal to 0.495 doesn't suffice. Why? That you can see here, the vortex which was causing that solution breakdown, this vortex keeps on growing unphysically, continues to happen. So here is a case, actually I think it's a sixth order filter. Yeah, it's a sixth order filter. The filtering direction, this is another issue that I would like to bring to your attention. It's a two-dimensional flow problem, right? So we have a radial direction and we have azimuthal direction, and the filters that we have talked about, they are all one-dimensional filter. So what we could do is we could of course apply it in the azimuthal direction, then we could also apply it in the radial direction. What happens is, here you are seeing some results of azimuthal filters, but a sixth order filter with a value of 0.495 for alpha does not suffice. At the same time, if you apply a second order filter and take the same value of alpha 0.495, what you notice that you can compute indefinitely. Okay. How good is the result? Now that's a very valid question, because the offending vortex which was causing the numerical breakdown here in these two cases attenuates to this. This is a much more weaker vortex, but it also has a very funny attribute to the solution. The vortex has been stretched in the theta direction, because that is the direction along which we are doing filtering. So if I keep doing azimuthal filter, I may get around the instability problem, but then the vertical structures would take some unphysical attribute, like here you can see this vortex has been detached already, and this vortex has also been stretched in the theta direction. So these are some of the issues that one needs to worry about. And the another thing that happens is there is no need for you to do the filtering at every time step. So you can do it infrequently, so that this frequency of filtering itself is another parameter at your disposal that you could make use of. So what is being seen here is the solution that we are showing for another case. This is a milder case. So here we could compute without any problem. You see, the amplitude has been reduced from 5 to 2, and the frequency has also changed to 4, and the unfiltered solution is shown here. Now if you start applying the filter in this frame, you are seeing that a second order filter with alpha equal to 0.4 has been applied, and the interval of application of filter is about every 1000 steps you are doing it. Now what happens? What happens is that if I do infrequent filtering, then the basic numerical method has an amplification factor which is given by the first factor on the right hand side, Gj, and if I would have done it at every step, I would have multiplied by Tj. But since I am doing after n time step, so the resultant amplification factor would be Gj of the original method times the transfer function raised to the power 1 over n. So you could actually reduce the intensity of filtering by doing infrequent filtering, right? That is what is being suggested here, and you could apply this procedure for any order filter in any direction. And That is what is shown in this last 3 frames. Suppose I try to solve the problem using a second order filter and take the value of alpha same as 0.4, and if I keep doing the filtering at every time level, this is the solution that you get. And I told you that if you do a azimuthal filter, you see this unphysical attribute, the vortices are stretched in the theta direction, and that is what you are getting. So, you are getting a so called stable solution, but not necessarily a good correct solution. If you keep filtering every 10 steps, that is this frame that you are seeing here, well, you can see a little more features coming out. Those unphysical stretching in the theta direction has been prevented somewhat, but it is still not completely gone, because you see those vortices which are all there, they are all absent in these 2 cases. So, filtering actually removes signal also. So, you have to keep that in mind. And then of course, when you increase the filtering frequency further, you do it every 100 steps, well, you start recovering back some of those lost signals, but it still you see there is missing structures. Whereas if you increase it, increase the frequency 10 times, that is you are filtering every 1000 time step, well, you can see more or less the structures are there, but they are much more weaker because of the factor that we are applying a filter. Please do understand that alpha equal to 0.4 is quite a strong filter. It's not a very small quantum of filtering that one uses. Now, having talked about the frequency of filtering, here is some results where we are talking about the direction of filtering. Once again, on top you have the unfiltered solution for the case just now we have seen. At a different time we are looking at, and now instead of applying a second order filter with alpha equal to 0.4, which actually makes the solution totally unphysical here, we decide to take a higher order filter, a 6th order filter, and also take alpha larger at 0.495. And what we need to look at is what we get if we do a filtering in different direction. For example, this one here we have used a azimuthal filter. So, basically the filtering is done only in the theta direction, and you can see there is some effect of the solutions. There is a wrong speed of propagation of this vertical structure. The strength also changes, the speed of convection of the vertical structures changes. However, near field structure are modified less, but they are indeed modified, but somewhat less. Okay. Now, if you switch over from a azimuthal filter to a radial filter, and you start from the cylinder surface all the way in the full domain in the free stream, then you get a solution which actually looks like what you have in the unfiltered solution. So, basically it tells you that you have to understand the physics of the problem, because what happens, the flow is coming from left to right, and then a boundary layer kind of forms, and that is separated by this rotary oscillation. However, if you now apply a filter in the theta direction, it kind of performs a mixing operation in the theta direction, right, and that mixing, numerical mixing, actually prevents separation, and that is what you have seen here, that you would not have to worry about numerical separation at all. The results are wrong, that is a different issue. Whereas, so this basically counteracts the action of rotary oscillation in the flow. Here the physical mechanism of the flow is determined by this rotary oscillation, and if I now filter in the theta direction, I am actually trying to take out the effect of rotary oscillation. Whereas, if you do a radial filter, you see that that action of rotary oscillation is not interfered that much, and that is why you can see that you get fairly a decent result. Okay. And of course, you notice that this filtering operation itself is done over the whole domain. So, you take all the points together and then you do a filtering. So, it does matter at times that whether you are doing the filtering from the cylinder to the free stream, that is going from the surface to outwards, or from outside to the cylinder. Okay? And you can see there would be some differences. And why would that difference be? That is because you are solving a tridiagonal matrix equation, and it does depend on the operation accumulates those errors, round of errors, right. If I go from j equal to 1 to n, then I have a one sequence of error accumulation, and if I go from j equal to n to 1, I have a different features. So, there are some minute differences, but which is not seen in these two frames. In a sense, it is good that at least for a problem of this kind, you do not need to worry tremendously about the direction of radial filter, but for some combination of physical parameters, this might affect the solution also. So, basically this is a kind of a portrait which will tell you how you are doing as compared to what people may have noticed in an experiment. This is an experiment done in France, published in JFM in 2006. Nice experimental visualization pictures. This is the cylinder performing rotary oscillation, and you see nice vertical structures. These are not like your Karman vortex trees. So, that is what you can see very clearly. The vertical structures are interleaved, they are all connected together. That is exactly what you actually get if you solve it with a lot of care, and care is done in this way, taken this way. This is quite a fine grid calculation in the middle column. So, you do not have any worry of filtering to do. So, that gives you a very good match with the experiments. This is the kind of computation one would like to do, where your computation and experiments, they actually look rather very close to each other. Now, on the last column, we are showing some filtered solution obtained with a 6th order filter, and this is interesting because we have applied filter on the first 30 lines close to the surface of the cylinder with a value of alpha of 0.49, whereas the radial filter has been applied in the complete domain. So, yes. No, there is not. There is not. That is the whole intention, is to show that if you choose the parameters, choose the directions, okay, and choose the way you want to do, then you should not be seeing much of a difference. In this case, there are actually no differences at all. Okay. So, this solution that we have shown in the middle is to convince you, I mean, if you do not apply a filter, what sort of solution you should get. This is a stable case. This does not lead to instability. Whereas, if I do something what I shown you earlier, if I would have used a 2nd order filter, I have used the azimuthal filter all over the domain, then things would have gone pretty bad. But if you do a high order filter, and even if you apply azimuthal filter, you apply it very close to the surface only. Okay. And then that does not cause any problem, and of course, the radial filter is applied over the whole domain, and with a filter value that is quite drastic. 0.45 is quite a strong filtering, but even then you can see there is no difference at all between these two sets of results. So, basically my intention is to sort of convince you that choose a filter correctly, and it would work to your advantage, and it would not lead to unphysical results. It is not somehow to get so called stable solution should be our goal. We need accuracy, and that is rather important. Okay. Now, this is something which we done in very recent times. This is the only work that has been reported so far. What we do is what we had done earlier for central schemes when we were developing compact schemes. We realized that sometimes numerical instabilities can be cured by upwinding. So here we tried to develop an upwind filter, Yogesh did, and you actually add an additional fourth order dissipation term with a floating constant eta. That should be what we will call as the upwind coefficient, and that should give you some additional degree of freedom. And why we are doing it, I will explain to you. This is important because this is not just simply a another filter that you have. Now, what you are seeing is the transfer function of this upwind filter at different nodes, and for different values of the upwind coefficient. This is eta equal to 0.001. Both of them are. So top you are seeing the real path. The real path will tell you that how things are. The first and the last point, the variables do not change at all. They just remain same. Now, if you look at let us say j equal to 2 and n minus 1, you get to this value. Okay, that is this value, the lowest sets of points. And as you go inwards, it keeps improving. So filtering is restricted only to the high kh, and this imaginary part actually would add on to the dispersion property. That is what we have talked about. If you recall what we said, that g hat is g times t. Now, suppose I have this, of course, we will have this, right. G of the basic numerical method will be complex, so it has a real path, and let us say these are looking at a particular node, jth node, that is what we are looking at. This I should multiply with Tj. Now, Tj also has a real path, and it will also have an imaginary part. Now, what happens to your g hat real would of course come from here. Let me be consistent. gjr times. So this is the real path, and so basically you can see what has happened here is this I could call it gjr, and this I will call it at gji, right. Remember that with the original method that we had, that defined your numerical phase speed through that beta j. Beta j was minus tan inverse of gji by gjr, right. So now what will happen here, you are after filtering, you are going to get this. This will change because the real and imaginary parts have changed, and that would be this tan inverse g hat of gji by g hat of gji. So that is what happens. So you can see if you have a transfer function with the imaginary part, then you are going to see that beta j and beta hat j, they are not same. But you can very clearly see that if Tji is identically equal to 0, then you will get beta j should be equal to beta j. So there is no change in dispersion property, because that is what eventually this defines your Cn by C and Vgn by C. If you look at your old notes, you will see that that is what you get. Cn by C is beta j by k delta t. Remember that expression that you have. So now things do change. So what happens is the two ways we can bring in the transfer function to become complex. One is of course this boundary closure, and the other one here is by design. We are purposely introducing a upwind filter which will have a imaginary path and which will show you this kind of a behavior. So, you will see that TJI has this kind of a property, and what does it do? That is what we like to see. Now, the previous case was for a eta equal to 0.001 and alpha was at 0.45. Here we are basically seeing the effect of real path for different upwind coefficients, and you can see it's got quite a bit of a control for us, because if I take eta equal to 0.01, I can see the filtering operation starts from a rather a moderate value of kh of 1 itself. Whereas, if I keep reducing the value of eta, the filtering gets delayed to higher kh, right. So, this is what you see at 0.45, alpha equal to 0.45. If you increase alpha to even higher value of 0.485, you will see that this is further delayed, the filtering action for lower values of eta. So, basically it gives you a confidence to really be able to have another parameter by which you can perform. Now, these are the corresponding imaginary part, and you can see the kind of things is that larger values of eta actually brings in a very strong value of the imaginary path, and that can change the dispersion properties significantly, very significantly. Whereas, smaller and smaller values of eta, the effects would be marginal and restricted to very high values of kh. So, having gotten that lead, we could basically define the benefits of upwind filters. We have seen that problems arise due to numerical instability near the boundary and excessive damping. This we could rectify by using upwind filter, and we also can allow a controlled amount of dissipation in the interior, and the absolute control of this allows one to really perform what is called as a subgrid scale model used for large eddy simulation, a very specialized branch of computing which has been in use for many decades, but with this kind of analysis now we are seeing a better explanation of the same. Okay. So, basically these subgrid scale models are related to that part of the flow which you are not resolving because of your grid size. So, to be not able to resolve that scale is equivalent to adding some having some extra stress, and this is what is attempted in this subgrid scale stress models. It is a fertile area of research, but let us not worry too much about it, but let us see what we can do if we look at a central filter versus an upwind filter on the right. Okay. Now, you are seeing basically the numerical amplification contours, and as you can see that there is not much of a difference between the two, not much of a difference between the two. Only thing is, with the upwind filter, let us say this 0.999 value has come slightly below 1. Okay. Earlier it was above 1. So, there is a marginal difference that you see. However, what was intended in doing this exercise was is given in this figure. If we used a central filter, then we identified a region of Q waves here, shown by this shaded area. So, this is your VGN by C equal to 0 line. Now, what you do is you keep the same filter coefficient 0.45, but use a upwinding of the filter. So, eta becomes 0.001, and then what happens? Then you see what happens is that this 0 line actually turns back, and then you have a region of MC as shown by this green shaded area on the right, for which there is not going to be any Q waves at all. Okay. So, this is something that was intended, that was the whole motivation, behind designing this upwind filter, and it just does show that you have a very narrow window, but you do have where you will not suffer from that extreme dispersion effect of Q waves. So, this is one thing that was achieved, and this we have seen before. This is another example, a tougher case, an aerofoil section which looks like this is exposed to a flow coming from left to right. So, this is like a normal flat plate type of geometry, and you do get very, very significant vertical structure originating from the ends of this aerofoil, and there are some comparison of results. Very high order filters have been used, 6th and 8th order filter in the azimuthal direction with alpha equal to 0.48, and these are the corresponding experimental visualization. It's very difficult to visualize this type of flows. So, the aerofoil is somewhere there, and this is the vortex that is shed from top, and this is another vortex that is shed from bottom. So, there is some kind of asymmetry of the shed vortices because of the asymmetry of the geometry itself. The top side is rounded, whereas the bottom side has got a very sharp edge, and the sharp edge actually brings about a much more diffused larger vortex, whereas the top surface has additional secondary separation occurring from on the surface itself, where this is very well defined. In fact, if you have those of you who do not belong to aerospace engineering, you may have wondered why the wing shape is like this. It is for this, that if you have a sharp trailing edge, you can actually force the flow to change locally there, whereas if you have a rounded edge, then the effects are diffused and it can actually cause a lot of unsteadiness, whereas this kind of sharp change in the trailing edge actually helps in a better performance of the wing, and that is why this is shaped like this. This is very wrongly understood, that aircraft flight is more like a swimming of a fish than flying of a bird, because the physics is totally different. When a bird flies, it actually flaps its wing, so it is a basically unsteady motion, whereas a fish glides through in the water. And if you look at a cross section of a fish, that would look more like this than if you take a section of a bird's wing, that would look like this. Anyway, the whole idea is this is again a very tough problem to solve, and which one could solve here by filtering with both. We have done it with azimuthal filters as well as upwind filters in wall normal direction, and some of these results are shown here for different time. But let me just simply close this discussion by looking at what we should be doing. We must develop a strategy that we have to find out a optimum filter. So, that optimal filter should be a combination of azimuthal filter that is applied close to the wall, and whereas in the wall normal direction you would have a non-periodic filter. See, azimuthal direction is a special direction because you have a perfect periodicity of the problem, right. So, you do not need to worry about this so called boundary closure. So, what happens is many a times people are very much attracted to use filter in the azimuthal direction because it is easier, you do not have to do additional problems, and then it is also has the property of retaining its property uniformly across all nodes. However, we have seen azimuthal filters has this tendency to change the physical nature of the flow. So, what you should do is basically apply azimuthal filter, which can be a central filter, but apply it only close to the wall, whereas the radial direction you have to use a non-periodic filter, and a upwinded filter is found to be the best I do not wish to go through this second point. It is something to do with computing fluid mechanics. So, let us not worry about it. Third point also, as I told you, it actually circumvents sometimes to do those fancy turbulence or subgrid scale modeling. So, this is a very good tool for one to learn and use it imaginatively, and you could also note that whenever you use non-periodic filter, you still have the problem of numerical instability near inflow and excessive damping near outflow. This has to be investigated, analyzed, and sorted out upfront. So, that can be worked out by using Upwind composite filter, which actually even allows you to add controlled dissipation in the interior. Upwind filters has better dispersion property. We showed that it can circumvent Q wave formation, and this approach of using Upwind filter does not require using different equations in different parts of the flow. This is one of the problem with large eddy simulation or direct eddy simulation people use. Okay, so I think we'll stop here on this, and I would like to go into the new topic, which is going to be on finite element method. So, basically it is our way of looking at this very special branch of computing. Finite element method is all pervasive. People like to know more about finite element method, but we have kept our focus intact on the scientific computing aspect of it, which is often not very well understood by many. Let us start by discussing about the various things that we know of, that we have focused most of our attention in whole of this course on finite difference methods. One of the problem that we have noted is it cannot, well, we have not noted because we have not talked about geometry aspect. We did not do anything about grid generation, etc., etc. That is a separate sub branch of computing, but finite difference are essentially more difficult to use on complex geometries. However, they have excellent resolution properties, and we have seen that finite difference methods, when well designed, can produce results which are extremely accurate, which are otherwise not possible by other methods. For example, we have finite element and finite volume methods, which are extremely attractive in handling complex geometries, and therefore boundary conditions becomes easier to apply. Specifically in finite element method, what you do is you break down the computational domain into smaller subdomains, and on each of these subdomains you approximate the governing equation by either variational methods or by what is called as a weighted residual methods. Okay. Calculus of variation is a very classic field. It started off with Euler, and lots of people have contributed. Unfortunately, when it comes to some special branches of computing, like in fluid mechanics, we do not pay much attention to variational methods, because the variational principle does not exist when you are looking at dissipative flows. For example, the governing Navier-Stokes equation does not allow you to develop a variational method, whereas the complementary aspect of it is via this weighted residual method. That could be quite easily done, and we will spend time talking about the next 4 days that we have at our disposal. Now, what you are trying to do is in FEM, you take this smaller subdomains, and in the smaller subdomains you try to fit the solution locally by simpler polynomials. That is the essential idea. So, what you have a big problem, you break it into smaller pieces, and then on each of the small pieces. You locally fit solutions by polynomials and try to find out the coefficients in this polynomial. That is essentially is done. So, basically in FEM, it would appear that overall solution is approximated by a local representation, which is different from global method. So, basically let us say if I have say some unknown u of x, I could write it by let us say Fourier series, and I could write it as u hat of k, and I could write some let us say k j, right, and here of course j could go from 1 to infinity in the actual case. This is what you know what you do in a Fourier spectral method. So, this is what is called as the Fourier spectral method. So, what you keep doing is of course you cannot accept a infinite series. So, you will stop at some finite number of terms, and your intention would be in a problem to be able to find these Fourier coefficients. Okay. What you notice in this global method, so this is a kind of a global method. Why do we call it a global method? I will explain. A global method is one where if you make some kind of a change, then that effect is felt globally in the whole domain. So, for example, if I change it from n to n plus 1, I have just added one more term in the Fourier representation. You would be surprised to see that this quantity will change across the whole scale. That's your global method, right? That's what we are saying, that let us say if we use a spectral method, this is a global method. But we have already seen, we are now more or less convinced that if we take a Fourier spectral method, what do we find for Cn by C is equal to 1, Vgn by C equal to 1. So, spectral methods are very, very attractive. However, they have some restrictions. What is the main restriction? The main restriction is, as we have written here, the problem has to be periodic, right? If we are summing by Fourier series, it has to be a periodic problem. So, it so happens that many physical problems, this imposition of periodicity lends itself to some sort of a unphysical attribute to the problem. So, not all problems can be well, most of the problems cannot be replaced by a periodic extension of the same problem. Okay. So, that is one thing. The second thing is, of course, in Fourier method, you end up working in the physical domain itself. Okay. Suppose I am looking at the problem in the Cartesian frame, then I stay there, and I am also forced to use equal spacing, and that is a major constraint. Whereas, in contrast, what you can do in most of the other computing methods, we have seen all of them suffer from various sources of error. That is what we have spent the whole course almost talking about, various sources of error, and all these other discrete methods suffer from those problems. Okay. And what happens is, of course, despite that we live with them, is simply for the reason that we can actually handle problems which are not restricted by the constraint of this special type of global method. We can talk about non-periodic problems, we can talk about non-uniform spacing, where we need more accuracy, we can cluster more number of points, where we do not, we cannot. So, this is something that we really need to appreciate, and that is one of the reasons that finite element and finite volume method enjoys its reputation of what it is. Let us briefly discuss about what these weighted residual methods are. So, that let us talk about a problem. As evolution equation is written like this. This L of u could be any problem that you talk about. Let us say you have a space time dependent problem, you perform all the spatial discretization. At the end of the spatial discretization, you will have a time varying equation of this kind. Okay. And let us say this talk about a one dimensional problem for simplicity. X belongs in a domain omega, and for all the problem starts at t equal to 0. So, you are interested in finding out the solution evolution, and the initial condition is given by u0 defined everywhere, and in addition you would have the boundary conditions like what you did in your second assignment. You have time dependent boundary condition at the boundary defined as delta omega. Okay. Now, what you need to do in developing a weighted residual method is to start with defining a trial function. So, the numerical solution we indicate by subscript capital N, basically that defines how many terms we are taking. We are showing it this trial solution to be composed of two parts. One is here CJT times UJX, and there is this additional term UB of XT. What this UB of XT is, that is a special function that is used there to specifically satisfy the boundary condition. You see, we are not going to do periodic condition, this will be non-periodic condition. So, that boundary condition would be given to you as has been given in 3, like f of b as a function of time. So, this second part of the trial solution actually helps you in satisfying the boundary condition. Okay. Whereas, at the boundary this uj's are 0. So, that this exactly satisfies the boundary condition, right. Now, these functions are called the basis function in this series, that summation term, which has a, let us say, time dependent coefficient Cj of t times a space dependent function. Now, these uj's are the basis function, and they are such that you can satisfy the prescribed boundary condition, but that would not satisfy the initial conditions and the governing differential equation. So, that means what? You will have to use equation 4 into the governing equation and try to see if you can derive some relations among all these CJs. I think we will continue with this in the next class. This needs a little bit of understanding how these things work.